Take a look at this. Vertical landing. Smooth. Sexy. No catapults. No arresting wires. This is the F-35B. Why is the United States Navy struggling with electromagnetic catapults on the Ford? Why not scrap it all and just use the F-35B? It takes off vertically. It's simple. It's cheap. On the surface, it sounds like a stroke of genius. And the rest of the world is doing it. Look across the pond. The Royal Navy. They bet their entire fleet on the F-35B. The HMS Queen Elizabeth. 65,000 tons. No nuclear reactors, no catapults, no wires, just a ski jump ramp at the bow. Simple, effective. Or look at our own fleet, USS Tripoli, an amphibious assault ship transformed into a lightning carrier. The F-35B works perfectly on it. So why does the $13 billion supercarrier USS Gerald R Ford say no? Why does the most powerful ship on the planet reject the most flexible aircraft on the planet? A plane that both the British and the United States Marines adore. The answer isn't politics or arrogance. It is geometry. Look at the cross-section of the F-35B. To hover, it has to carry a massive lift fan right behind the cockpit. In the eyes of an engineer, that fan isn't a miracle. It is a void. It consumes the space of the two things that determine life and death at sea: fuel and firepower. That fan chokes the internal weapon bays. You lose the space for 2,000-pound heavy anti-ship munitions. You are forced to trade stealth for ammo. When the F-35B is in cruise flight, that fan is just tons of dead metal. It doesn't help you shoot further. It makes you weaker. The British accept that trade-off because they defend the European coast. But the United States Navy? If you put the F-35B on the Ford, you've just turned a nuclear fortress designed for ocean dominance into a coastal helicopter pad. It's like using a nuclear reactor just to power a toaster. And that is when we have to look at the reality of the Lightning II family. Look, the F-35A has become the standard for air forces globally. The F-35B has opened a new era for small fleets and amphibious ships. But the F-35C? It is an exclusive anomaly. It's not for the masses. It is operated solely by the United States Navy on the strongest supercarriers in history. Why? Because it is the only variant that deletes that damn fan to pack in fuel. The only variant with wings large enough to dominate the Pacific. But here is the real joke of physics. The Ford was born solely to serve the monopoly of the F-35C. The F-35C was born solely to operate on the Ford. But right now, they cannot touch each other. Look at the Ford's deck today. Empty. No sign of the F-35C. The world's most modern ship is rejecting the world's most modern weapon. Why? Because this plane runs 700 degrees hotter than the ship can handle. Because it is louder than human survival limits. And because it demands things that the engineers who designed this ship in 2005 never even imagined. We built a cage in 2005 for a monster from 2025. And now, the cage is cracking. We are about to dissect this $13 billion paradox, bolt by bolt. If you appreciate raw engineering over political headlines, hit subscribe to join the inspection team. Now, how do you fix a physics error on 100,000 tons of steel floating in the middle of the ocean? Welcome to the synchronization gap.
We agree that the F-35C is mandatory. There is no alternative.
So why was the Ford, the most modern ship, delivered without being ready for it? Many call this poor planning. I call it the cruelty of materials science. Look at the shipbuilding process. When you lay the keel for a 100,000-ton ship in a dry dock, you are making a commitment in concrete and steel. When 10-inch thick steel plates are welded together, you cannot hit Ctrl-Z. You cannot download a software update to change the diameter of a water pipe or the location of a load-bearing bulkhead. This is a concept engineers call the frozen baseline. Rewind to 2005. That was the year the United States Navy locked in the Ford's hull design. At that moment, engineers had to make life or death decisions. Where do the wires go? How big are the cooling pipes? What is the generator output? The problem? In 2005, the F-35C was just a promise. It existed on CAD drawings. It hadn't flown. The most critical documents, called ICDs, interface control documents, governing weight, exhaust temperature, and power requirements, were still fluid. The Navy fell into a strategic trap called concurrency. They applied a design-build strategy. They built the shell, the ship, while waiting for the guts, the plane, radar, catapults, to be finished. It was a massive industrial gamble. They went all in on the bet that when the ship was done, the plane would be done, and the two puzzle pieces would snap together perfectly. They lost that bet. The CVN-78 ran faster than the plane. It was born before the final technical requirements of the F-35C were locked down. The physical difference of the finished C variant was a shock. The F-35C isn't just a repackaged FA-18, it is a completely different beast. Let's start with the first contact with the deck. The Navy calls it a flareless landing. Sounds gentle, but physically, it is a controlled crash. Pilots don't pull the nose up to glide down like in older jets. They drive a 30-ton aircraft straight into the steel deck. The 2005 hull structure was never prepped for the frequency of this violent surgery. And the moment it stops, the logistical nightmare begins. With its massive folding wings, it consumes space and forces deck crews to rewrite the entire ballet of aircraft movement that has existed for 50 years. But all those physical pressures are nothing compared to the invisible burden it carries: data. The F-35C is essentially a flying server wrapped in a stealth shell. It doesn't just thirst for JP-5 fuel, it starves for information. Before the engine can even roar, it needs to drink terabytes of mission data, threat maps, and real-time encryption keys. The fiber optic infrastructure and server rooms of the 2005 design simply didn't have the bandwidth to feed this digital monster. It's like trying to run a 4K game on a 90s dial-up connection. The result is a synchronization gap. The CVN-78 was delivered, but it carries an old operating system. To operate the F-35C, the ship is forced back to the shipyard in 2025 for a massive upgrade called PIA, Planned Incremental Availability. Do not be mistaken, this is not routine maintenance. This is painful orthopedic surgery, to cut out old steel and transplant a new nervous system.
People say the Ford is the strongest cage on the planet. But the problem is, the monster we locked inside breathes fire hotter than the hell the cage was designed to withstand. The war between steel and fire begins right here. Welcome to the harshest test, the thermal module. Don't look at the F-35C as an airplane. From a thermodynamic perspective, it is an industrial blowtorch with wings. The old FA-18 has two engines. The heat is split. It's breathable. But the F-35C funnels all 43,000 pounds of thrust into a single nozzle. When the pilot kicks in the afterburner, the exhaust temperature spikes to 3,600 degrees Fahrenheit. Recall your basic metallurgy. Steel doesn't need to melt into liquid to fail. At the 1,000 degree threshold, steel starts to lose its hardness. At 2,000 degrees, it gets soft as clay. With the 3,600 degrees Fahrenheit blast of the F-35C, the problem isn't the deck disappearing. The problem is that it will permanently warp under the 30-ton weight of the aircraft itself. You cannot launch a jet from a deck that ripples like a potato chip. If you put an F-35C on an old catapult, when the pilot throttles up, the jet blast deflector behind it won't just get hot. The passive steel side panels will turn into candle wax. They will buckle, deform, and lose structural integrity before the plane even leaves the ground. The Navy's solution wasn't to add more steel. They had to change the ship's circulatory system. Engineers had to operate on every deflector, threading a vascular system made of Cu-Ni alloy inside. They pump cold seawater directly from the ocean into the core of the panels to absorb that thermonuclear rage. But the fire isn't the only thing being destroyed. Look down at your feet. The traditional epoxy non-skid coating, which has served us for 50 years, has surrendered. Facing the thermal shock of the F-35, it doesn't melt. It explodes. This phenomenon is called spalling. The deck surface flakes off in chunks, turning into sharp shrapnel ready to be sucked back into a $100 million engine. This is the moment we abandon the painting mindset and switch to the armoring mindset. Chemical epoxy is dead. Against the F-35's heat, it evaporates like water. The new solution is twin-wire arc spray. Engineers use high voltage to melt aluminum and ceramic wires, then blast them onto the deck with high-velocity air. When they impact, they don't stick like glue. They mechanically bond to the steel at a microscopic level. The result is a ceramic metallic skin, the only thing strong enough to stand before the breath of a dragon. But even if the deck doesn't melt, the pilot is in trouble.